everybody. Today we are going to continue our discussion on supramolecular photochemistry. So we saw in the last lecture that the co-crystallization process using 1,3-dihydroxybenzene is able to now bring the double bonds in bipyridine bis 4-pyridyl ethylene into the close proximity, and now on irradiation they are able to undergo the 2+2 cycloaddition reaction to give the photodimer. Along the same way, people have used now thiourea also as a template to achieve the 2+2 photocycloaddition reaction. So let us now look at this dimerization process where thiourea serves as a template. So we have the two NH bonds, and this forms hydrogen bond NHN. NHN hydrogen bond, and this side also we have got and so you see here that the thiourea molecules itself form this hydrogen bonded tape structure, and then we also have now the next set of these molecules which are going to come close to each other, and on irradiation they will now be dimerization, photodimerization of the double bonds to give you the photodimer. So we can now pre-organize these reactant materials into suitable geometrical orientations such that the dimerization can take place in a facile way. The double bonds are now in the close proximity. The separation is between 3.5 to 4 angstrom. The desired distance is achieved, and hence dimerization proceeds. Now the next thing which we need to keep in mind that the environment which is being created, or the template which is being created, is able to bring about certain reactions which otherwise do not take place in solution. So most of these active species which contain isomerizable double bonds, they do not undergo the cycloaddition reaction in solution. However, when they are actually brought inside a reaction template, then the reactant molecules come close to each other and they are able to adapt the right orientation, and then dimerization reaction proceeds in a facile way. When this work was being performed by Gerhard Schmidt, he also proposed the concept of minimum movement of the molecules during the process of photodimerization. So when the dimerization process is taking place and the product formation is happening starting from the reactants via a particular transition state, which involves activation of the molecules in the ground state by light, taking it to the excited state, the reaction happens, and then the product formation takes place. During this entire chain of events, there may be changes in the shape of the molecule. If the shape of the molecule is large, then the lattice might not be able to accommodate this change, and product formation might not take place. However, if the product formation happens in a way that the final product involves minimum change in the shape, and the final shape is able to accommodate, is able to be nicely accommodated in the host structure, in the parent lattice, then the corresponding reactions will proceed in a facile way. So the environment has got a very important effect on bringing about these cycloaddition reactions of photodimerization. So let us look at the effect of the environment. For example, when you have a reactant molecule, it will give you the products P1 and P2. Say one is P1 and one is P2 of different shapes. So the shape change can take place and there is no problem in gas phase. In the solution phase, you have the reactant molecules and you have the solvent molecules, and we can have this as the product and we can also have this as the product, and the solvent molecules can now change their orientation, they can relax fast. So, relaxation of solvent can happen, and this allows for product formation in the liquid phase or the solution phase. And then when you have a solid, the solid has got a well defined architecture. For example, the crystal structure has got finite voids, and now you have got the reactant molecule here, and there are two possibilities. And for example, because the void is same, it can change shape to this one, okay, but this change will not be accommodated, because here you see that the shape becomes sufficiently large that actually it now creates sterics between the boundary of the template, that is the boundary within which the reaction has to take place. If that boundary is crossed, then it puts a lot of stress on the crystalline system, and therefore this product formation does not take place. Only this particular product, say for example P2 is formed, P1 is not formed, and therefore this rigid environment only allows certain shape changes. And this enclosed space is referred to as the reaction cavity. The enclosed space is referred to as the reaction cavity, that is the volume which is available at within which the reaction is supposed to take place. This size is small in case of crystals and cyclodextrins, which have got the intrinsic voids, and the size is large if you have got micelles, zeolitic structures, or silica, which are large three-dimensional molecules. And what has been observed, that if you have isotropic liquid, then the free volume available is mobile. It's like it's a mobile phase. The solution phase is a mobile phase. However, in crystals or organized media, it is essentially immobile. Okay, so we have got quite a limitation in terms of the free volume which is available. So let us look at this particular representation. So we have got the reactant molecule, and this is the this is the free space, which is available for the reactant molecules to interact and with each other. This is the boundary which cannot be exceeded. This region is outside and this is inside the reaction cavity. This is the overall diagram depicting a reaction cavity, and whatever you see here now, this region which you see here is the free volume, and in this case you can see that the shape of the size of the free volume is important. And what is the overall shape of the free volume? In this case it is more like a spherical free volume shape, but this spherical shape can also change as a function of the template which actually creates the reaction cavity. So we have this boundary, and this boundary is what is the reaction template. So we have a template which is created for the reaction to take place, and this defines the reaction cavity. So it is also to be kept in mind that during the process of supramolecular dimerization, particularly in crystals, there will be a minimum atomic motion. If the atomic motion is large, the distortion is severe, then the product formation will not take place. However, if the product formation involves minimal atomic motion or minimal rearrangement of the positions in the final product, the reaction proceeds in a facile way. So the free space or the free volume allows for the necessary tolerance to be present in the system for the chemical reaction to take place, and this model is referred to as the Cohen's reaction cavity model. Cohen was a scientist where Gerhard Schmidt was working, and after the untimely death of Gerhard Schmidt, it was Cohen who actually took his work forward, and then he started looking at the overall features of supramolecular reactions, and then proposed this reaction cavity model. So we have got in crystals, we see that the free volume is essentially immobile, whereas in isotopic liquids it is mobile. And so basically in crystals, the template or it is a very rigid and organized phase. So in case of crystals, we can say, in case of crystals, they are rigid and organized, whereas in the case of micelles, all liquid crystals, LCs that we have discussed, these have got flexible structures, and free volume may become available as the reaction proceeds. So it is to be kept in mind that this free volume also has to be optimized. If you have a lot of free volume and lot of free space, like you have in case of gaseous reactions or in case of liquids solution phases, then you might not get the desired selectivity. At the same time, if the void space is free volume is very small, confinement will not happen, and then the reaction will not take place because there is no free volume available. So in this regard, we would like to now look at the fact that there are now, depending upon whether we have rigid and pre-organized cavity or whether we have got flexible cavity, we can now define reaction cavities as hard and soft reaction cavity. So, and then so crystals and zeolites have the hard reaction cavity, but micelles, liquid crystals, have the soft reaction cavity. Similarly, we have the proposal for time independent reaction cavity, which essentially does not change its shape during the process of the reaction. So as the reaction proceeds, the overall free volume shape, the shape of the free volume, the cavity, that does not change its shape during the process of product formation. So free volume cavity remains fixed as the reaction proceeds. So we have got, for example, we can, this is the reaction cavity and this is my reactant, this is my reaction cavity, and this is the available cavity free volume. And during the process of photochemical irradiation, we will see that now the product formation has happened, the product formation has happened, but the cavity free volume remains same. The cavity free volume remains the same. So in other words, this cavity free volume is intrinsic to the supramolecular system, whereas in the case of micelles and liquid crystals, we have got a time dependent cavity. We have got a time dependent reaction cavity, where we have initially, for example, we might have the spherical free volume. This is the reactant, and during the process of the photochemical reaction, again this is fixed, but now you see the free volume shape changes to accommodate the product. So it was spherical here, whereas here it becomes less spherical, more ellipsoidal type of cavity. So the reaction cavity is now quite flexible. It is soft. It is able to accommodate the changes which happen during the product formation. So that is what makes it flexible, and that is why we call it, this is latent. That is, it is available as per the requirement of the reaction. So this is a latent cavity, that is the cavity or the free volume will be available as the reaction proceeds, and that is why the nature of this cavity is soft or flexible, which can accommodate the product very well due to changes in the shape and the size of the product. The cavity is also flexible, so that the free volume can also change depending on the changes in the shape of the cavity as well. So in one case it is intrinsic, in another case it is a latent cavity which is available as per the requirement of the reaction. So and then there is another categorization of cavity, that is the reaction cavity we called passive reaction cavity, and we have got active reaction cavity. So here in case of passive reaction cavity, you see we have got the host structure, which is either the crystal or we have got the supramolecular host case complexes. The interactions are weak and non-directional, or practically you can say that they do not exist. There are not much important non-covalent interactions between the guest and the reaction host, whereas in the case of active reaction cavity there exist strong and directional interactions between the guest and host template, and this can actually influence the reaction outcome in profound ways. So now we are going to look at some of the important applications of the reaction cavity model, which is able to bring about certain photodimerization reactions. So for example, what we would like to see, the next example is of dimerization of coumarin. Coumarin, as you see from the structure, this is coumarin. If you look at the crystal structure and the orientation of the coumarin molecules, on photo irradiation in the crystal, no photoreaction takes place, so it is a photostable molecule. However, when you actually template it with this chiral compound, C, EH, CH, OH, C, PHOH. Then on irradiation, it will give you the so you see here that now this is the bottom part and this is the top part. So we have got now the anti head to head arrangement. So you see that these are anti to each other and the head parts, they interact and form the photodimer. So what does this chiral molecule do? This chiral molecule actually creates a hydrogen bonded template which actually brings the coumarin molecules in close proximity to each other, and they interact by pi stacking interactions which are favorable here, dispersive interactions, and then photo irradiation is able to create the photodimer. So this can actually provide the necessary template by which the coumarin molecules can undergo photodimerization. Now let us take another interesting reactions, a set of reaction where we look at performing chemical reactions in micelles. So we would like to look at this particular reaction. N-butyl plus OAC R1, R1 is C5H11. Photodimerization, photo irradiation leads to the formation of these two possibility exists. I call it product A, I call it product B. This is 3N-butyl cyclopentanone. This is my heptanyl acetate. Now let us look at the reaction conditions and yields. So when you do it in methanol, this particular reaction, A and B, 0%, 100%. When you do it in cyclohexane, it is 0, it is 100%. But when you do it in the presence of a micelle, that is potassium dodecanoate micelle, you get 70% of A and 30% of B. So you are now able to access the product A, which is actually not formed at all when the reaction is performed in methanol or in case of cyclohexane. So there is a very profound role of the micelle, and we know that a micelle is a species which has got the polar heads and the non-polar part. The polar head is what is being solvated in water, and non-polar head is buried deep as a hydrophobic interior. So how does this reaction proceed? The reaction proceeds by bringing in the polar reactant molecules. So you have the polar parts and you also have the non-polar parts. So the non-polar parts of the reactant molecules now are buried within the hydrophobic core, whereas the polar parts are now brought into close proximity at the hydrophobic hydrophilic interface. So let us look at, so we have now got this micelle here. So you say this is the surface of the micelle, okay, and we have got the surfactant molecules here. So this is my surfactant molecules and this is my hydrocarbon chain. You can have say another one here, and now my reactant molecules are swimming in this particular micelle. So the reaction template or the reaction cavity is being provided by the micelle here, and I am now going to add. So this is my N-butyl chain, and I also may have statistically the possibility of another one here. Then I can have another one here, and now you see here that these two come close to each other and have the right orientation at the hydrophobic, and this is hydrophilic interface. So this is the water molecule, the polar parts which are actually solvated in a polar solvent, as we know. So the micelles which is present, the potassium dodecanate micelle, now at the hydrophobic hydrophilic boundary, these reactant molecules will react with each other to give you this particular product. So you can see the double bonds and the OSC and the carbonyl group, they are sent to each other, and that gives you the desired A product in 70% yield. So this orientational effect at the interface is brought about by these micelles, which allow for the chemical reaction to proceed in a very facile way, and thus micelles, which are actually supramolecular aggregates which are stabilized by hydrophobic as well as hydrophilic interactions, steer these chemical reactions at very preferred rates, and the yield actually is enhanced as well. So you are able to get those products which are actually not achieved in other solvent systems. Now let us take another example, very interesting example of photodimerization. In the solid state, in case of cinnamic acids. Okay, so we will compare in photodimerization in the solid state with aqueous solution. Okay, with aqueous solution. So we will now see that in case of cinnamic acid, when we do H nu irradiation in the solid state, no dimerization is observed. However, when you irradiate in aqueous solution, it undergoes cis trans isomerization, where R is equal to phenyl group. And when we actually have now a host, in this case we are using cucurbiturils 8, and do the irradiation in aqueous solution, then we are able to get in aqueous solution the photodimer, but we also have the cis isomer, and this is a head to head alignment. So cucurbiturils actually give the desired molecular template by which the cinnamic acid are able to orient themselves inside the cucurbituryl, which is actually functioning like a supramolecular barrel here, which provides the necessary confinement to the molecules, and they are able to come close to each other, and the dimerization proceeds in a facile way. Let us look at this. So we have got this barrel like structure, okay, and we will now bring in the, so we have the carbonyl groups which are present on the cucurbituryls, and we have now our reacting molecules. So we can now bring in So, you see that there are hydrogen bonds, OHO hydrogen bonds in this particular region, and these are essentially stabilized by the hydrophobic interactions. Now, see this very nice architecture. Both hydrogen bonds and pi-pi stacking interactions orient the molecules, which actually now promote the head-to-head alignment of the molecules. So, the head-to-head alignment of the molecules where the carboxylic groups now face each other because they are stabilized by strong hydrogen bonds. So, as I was telling you in the previous case that there can be an active cavity, there can be a passive cavity. So, this is an active cavity where there are strong hydrogen bonds and it will interact with the host template, which will pre-organize these which will pre-organize the reactant molecules, and then you will have the dimerization. So, the hydrogen bonds in the pi-pi stacking interactions orient the molecules, but it is actually the hydrophobic effects which actually stabilize this entire dimer inside the molecular vessel. So, you also have the role of hydrophobic effects which are stabilizing these pi-pi interactions via the hydrophobic walls of the host structure. So, this will lead to facile dimerization, and now you can put different substituents R here. When R is equal to 4-methoxy, then the percentage of dimer in cucurbiturils, I am writing it as Cb, in Cb, and the percentage cis product, it is 72%, 28%. When it is 3-OMe, then it is 72%, approximately 8%, and when it is 2-OMe, it is 83%, this is 17%. So, this is what has been reported in the literature, that we are able to achieve this photodimerization in aqueous solution in the case of cinnamic acid using cucurbiturils as a pre-organized host structure into which the molecules go, and in the reaction cavity the reaction takes place, the photodimerization takes place, which is templated by the active interactions, and hence the product is formed. So, in the next lecture we will look at some more interesting case studies where this cavity plays a very important role, and we will also see some cases where now because of the cage effect, unusual or unstable intermediates can now get stabilized for extended periods of time, and we will also look at some more interesting reactions which take place by photodimerization to form more interesting organic molecules. Thank you.